Okay, chapter 6 is all about circular motion, basically. So we get started with this problem. A softball pitcher is throwing a pitch. At the instant shown, the ball is moving in a circular arc at a steady speed. So that just means a constant speed. At this instant, shown in the picture, the acceleration is which one? Directed up, directed down, directed left, directed right, or 0 at this instant. So if we look at the picture, we can assume that in the picture, the velocity, so it says the acceleration is what we're looking for. We can assume that the arm is exactly horizontal. So that means that the velocity, from what we've seen, would be directed directly down, which means that the acceleration would actually be definitely not directed directly up, definitely not directed directly down, definitely not left, because that would be pulling it outside of the circle. And we know we have an acceleration in order to get the velocity to change. So the only possible answer is directed directly right. The acceleration would be going in towards the center of the circle. So the center of the circle is at the lady's shoulder here. So directed directly into the center of the circle. Centripetal acceleration is what we're dealing with here. So it has to be directed directly to the right. So that's what we're doing in this entire chapter is uniform circular motion. Now, we've seen the word uniform before. Uniform means constant something. So constant speed is what we're talking about here. So constant speed around the circle. We can't say constant velocity because the velocity is definitely changing. Remember, velocity is speed, so magnitude is the speed and direction. But because we're going around a circle, the direction is constantly changing. So we can't say constant velocity. We have to say constant speed. So the speed is staying the same as we go around the circle. All right, so uniform circular motion means constant speed in the circle as we go around. All right, centripetal acceleration. Remember, centripetal acceleration from before means center seeking. So the acceleration is always pointed directly at the center of the circle. And we have this equation here, this formula for centripetal acceleration. We're going to be using that one constantly in this chapter. So acceleration equals v squared over r. V is the speed squared over r. Okay, even though v is velocity usually, we're going to call that the speed. So an object's centripetal acceleration depends on both its speed and its distance from the center of its circular path. So the instantaneous acceleration, so the acceleration vector is also changing. The direction of the vector changes as the object spins around the circle. It's always directed toward the center of the circle at all points as it moves around the circle. Okay, so very straightforward equation, and also hopefully the concept is also easily understood. So now, in this example, we have the car rounding the corner. The car is turning the tight corner at a constant speed. This is the top view of the motion as shown in the picture. And the velocity vector for the car points to the east at the instant shown. What is the direction of the acceleration? So we have the compass here. North is pointing up in our picture. East is to the right. So what is the direction of the acceleration? The acceleration would be always toward the center of the curve. The center of the curve is sitting right here. So the acceleration would be pointed in the direction of south would be the answer. Okay. So it says, note, the car in the example would not continue in a full circle. Unless we were on a roundabout, that's not how roads operate, right? We just have a curve that achieves the amount of curvature that we want, and then the road straightens out. However, at the instant that we're showing, the motion of the car is following a circular arc. So while we're in that circular arc, we are seeing uniform circular motion. Okay, so that's something that we can do, is we can model uniform circular motion while we are in a curving road. So that's an important note there. Okay, so now other important things that we're going to be dealing with in this chapter are period, frequency, and speed. So periodic motion is something that happens when we have a repetitive circular motion going on. Okay, so a period is the time interval that it takes the object to go around like a circle one time. The amount of time it takes something to achieve one full revolution. Okay, so one revolution has an abbreviation, 1 ReV, 1 rev. The symbol for period is a capital T. Now this could be confused with tension, so you have to be kind of careful. We use a capital T for period, we use a capital T for tension, so you have to just understand what it is that you're talking about there. Period is capital T for us. Okay, so remember, period is the amount of time it takes to go through one full revolution. Now, we may have seen a graph that was showing the position of some object in circular motion as time went on, and that graph might have looked something like this. Okay? Now, the period in a graph like this would be measured from peak to peak, or you could go from trough to trough, like so, or you could look at maybe this was the starting point, and then you would go to the next starting point. Okay, so as long as you're going through one full cycle, so this would be one full cycle here. See how we're going right back to what the graph looked like when we started. The graph was starting at like this center point and then increasing, and here we are again at the center point where we're increasing. As long as you're going through one full cycle, then you have found you have gone through one full period of motion. Okay, so anyway, that is how you would find the period. You'd measure that distance from peak to peak, or from trough to trough, or from starting point to starting point. Okay, so frequency is the number of revolutions per some unit of time. Could be seconds, could be minutes, could be hours. Okay, for example, miles per hour. How many miles do I get to go in 1 hour of time? Meters per second. How many meters do I go in 1 unit of time? In this case, seconds. Okay, so that's frequency, the number of revolutions when we're talking about circular motion per unit of time, such as seconds. Okay, frequency is exactly the inverse of period. So if I know the period, then I simply go 1 over the period and I have the frequency. Now, the units of period would be seconds, okay? So this might be seconds if we're in the standard units of time. So standard units would be seconds. So then frequency would be 1 over seconds, or inverse seconds. Seconds to the negative 1 power, okay? Then I talk about that down here. So note that revolutions are actually not a true unit of measure. We would not say like revolutions per second or something. It would just be seconds to the negative 1 power. So they're just a count. It's a count of the number of times some event has occurred, like the number of times the wheel has rotated around. So we actually don't include revolutions as a unit. So therefore, the unit of frequency is just inverse seconds. You may see revolutions per minute, but usually you'll convert to inverse seconds before calculating anything, okay? Revolutions does not count as an actual unit. So we continue, and we have this. So relating frequency and speed. So in the picture, we have circular motion, some object here traveling along this way. So we see the velocity vector moving in this direction. So the object is traveling counterclockwise. Now, that's an important point that we should probably talk about. Things rotating in a counterclockwise fashion, so rotating counterclockwise, we call that positive rotation, okay? And actually every example that you've seen, let me think about that. Okay, so the couple examples that you've seen so far, with the exception of the car, have been rotating counterclockwise. And that's because counterclockwise rotation is a positive rotation. All right, clockwise rotation, so clockwise rotation would be a negative rotation. All right, now there's a good reason for that. And that reason, as far as I can tell, I could be totally off on this, but this is how I remember it. If I have a standard coordinate system, x is where I would start. The positive x-axis is where I would start if I was trying to create an angle. And then how would I create my angle if I was to grow an angle from 0, if this was my 0 angle right here on the positive x-axis? Well, the answer would be I would grow my angle from the positive x-axis up, okay? And because I'm growing my angle from the positive x-axis up, if I wanted to make it bigger, I would go more. If I wanted to make it even bigger, I would go more. And what am I doing? I'm growing that angle here by rotating that ray around in a counterclockwise fashion. So that's kind of how I remember that rotating counterclockwise is positive, because I'm growing a positive angle from the positive x-axis by rotating that ray around in a counterclockwise fashion. I have no idea if that's the correct answer as to why rotating counterclockwise is positive, but that's the best I have been able to come up with as a reason. So that could actually be the right reason. I don't know, but that's how I remember it. So anyway, rotating counterclockwise is positive. So this object that we have up here is rotating in a positive direction because it's rotating counterclockwise, okay? So at this moment in time, we have a velocity vector pointing exactly directly to the left, okay? So as it rotates around, in one period, so I'm reading the words right here now, in one period t, the object travels around the circumference of a circle. And the circumference of a circle, we know the formula for that, circumference equals 2 pi r, as it's written right there, right? So the distance that it has to go around the circle one time is 2 pi r, whatever the radius is, we don't know, okay? So the distance around, for it to go one time around, is 2 pi r, okay? That would be like a delta x if we were just working with linear motion, okay? Now, we know the time for one revolution, the period, and the distance traveled, the circumference, okay? So we can write velocity. We know that distance equals rate times time, okay? So if I want to talk about the velocity, that would be the rate. So if I solve this equation for rate, I'd have to divide both sides by t. So I'd have rate equals distance divided by time, okay? So rate is the same as my velocity. Distance is like the circumference of this circle. That's 2 pi r. So velocity here, okay? And then distance is 2 pi r here. And then time is the period, how long it takes me to go around the circle, okay? So period is the time, okay? Now, if I simplify this, v equals 2 pi r over the period. Well, what's the period? The period is 1 over the frequency. So if I wrote that as if I wrote period as 1 over f, the leave it, change it, flip it idea would flip the frequency, 1 over the frequency in the denominator, into the numerator, and I'd have 2 pi fr. So that's where these two formulas here come from. So we have, in this line right here, we have two formulas that we can use to find velocity. We have v equals 2 pi r over the period, if we knew the period, and we also have v equals 2 pi frequency times the radius, if we knew the frequency, okay? So now we have two ways to calculate the velocity. Now, if we combine these formulas with the equation for centripetal acceleration that we saw earlier, acceleration equals v squared over r, right here, then we get new equations that relate the acceleration to equal either the frequency or the period for circular motion. And this will give us now three formulas to find the acceleration. We have the acceleration equals v squared over r, like we knew already. But now if I substitute Using frequency equation from up above, we have acceleration equals 2 pi frequency squared times r, after we simplify a little bit. Or I have this guy, acceleration equals 2 pi over the period squared times r. Okay, so now we have three formulas to find the acceleration. We can use all three of them depending on which information it is that we have in the problem at hand. Okay, let's take a look at this problem now. The circular blade of a table saw is 25 centimeters in diameter, so I immediately want to switch that centimeters to meters, and spins at 3,600 revolutions per minute. That's what RPM stands for. So I would immediately want to switch that minutes to seconds. How much time is required for one revolution? Okay, so how much time is required for one revolution? That's asking for a period. How fast is one of the teeth at the edge of the blade moving? That's asking for a velocity. And what is the tooth's acceleration? That's obvious what that's asking for, okay, acceleration. So we don't need to draw a picture here, but we do need to change some things around. So 25 centimeters to meters just moves the decimal 2 spots. So I have 0.25 meters. That's pretty straightforward. And then I have a frequency given, spins at 3,600 revolutions per minute. So that is a frequency. So F equals 3,600 rev over minute. Okay? Now I want to convert that to seconds. So per second, okay? So we're going to go times and get rid of minutes and introduce seconds. And there are 60 seconds in 1 minute. So the minutes are gone, and we're going to be left with per seconds. Now remember, revolutions does not matter at all, so I get rid of it completely. And when we do this, multiply it all out, we have 3,600 divided by 60. So this is going to wind up being 60 inverse seconds. Okay, and I should mention that there is another unit. Inverse seconds is the same thing as this Hz, and Hz stands for hertz. Hertz. It's a little bit cleaner looking. We can use inverse seconds like that because that works better with our units when we're figuring out our unit analysis. But in the end, if you have inverse seconds, if you're finding a frequency, inverse seconds ends up written as hertz. Okay, just so you know. All right, so now we have our frequency, and we want to find the period. It says how much time is required for one revolution. That is a period question. So we have this formula that says F equals 1 over T. I can solve for T by multiplying both sides by T and dividing by F. So this gives me T equals 1 over F. Very simple. So I have 1 over, the frequency is 60 inverse seconds. Okay, so my properties of exponents tell me that when I have a -1 or a negative exponent in the denominator, I just move it to the numerator and then the exponent becomes positive. So I have equals 1/60th of a second. Now, if I wanted to go to decimal on that, I really don't want to go to decimal on it, but if I wanted to go to decimal, 1 divided by 60 winds up being 0.017 seconds. Okay, so that takes care of the period. Now, how fast is one of the teeth at the edge of the blade moving? Okay, so that's looking for a velocity. So we need a velocity equation. We have a couple of them that we could use. We actually know the frequency. It's 60 inverse seconds, right? So let's use that one. But we also know the period. It's 1/60th of a second. So we could use that one too if we wanted to. It doesn't make any difference. So whichever one you felt more comfortable with would be fine. Velocity equals 2 pi times the frequency times the radius. Okay, so we have 2 pi times the frequency, which we calculated to be 60 inverse seconds times the radius, which they told us was 0.25 meters, right? No, that's actually the diameter. So we got to be careful. They told us the diameter. It's going to be 0.125 meters. Okay, so 0.125 as a fraction is 1/8. So we have 2 times 60 times 1/8. Well, 2 times 1/8 is 1/4. 1/4 times 60 is what do we get? 15 times pi. So whatever 15 times pi is, works out to, with significant figures, 47. And then we have meters and inverse seconds, meters per second. All right, so now let's see. How fast is one of the teeth? That was velocity. What is the tooth's acceleration? Okay, so acceleration equation. We know the period, we know the frequency, and we know velocity. We could use any of the 3 acceleration equations that we have. We can use v squared over r. Perfectly fine. We know the calculator's answer for velocity. We would use that instead of the rounded one. So I'm writing 47, but I'm using the calculator's answer instead. 47 meters per second, it's squared, divided by the radius, which is, remember the radius, 0.125 meters. And the calculator gives us something crazy, 765.3. This is meters per second squared. But now we have a significant figure. It's going to be 18,000 meters per second squared. A crazy huge number. Massive acceleration for the tooth on the edge of the blade. Pretty interesting, I think. Okay, so let's move on. In the Quasar Carnival ride, this is like the Gravitron ride, if you've ever been. I think they call it the Gravitron ride still. You're traveling around in a horizontal, like a dishwasher, not a dishwasher, like a clothes washing machine where the thing spins and spins and spins and squeezes all the water out of it. This is the same kind of thing. Passengers travel in a horizontal 5-meter radius circle, and then they basically get stuck to the side. The little slide slides up, and then you're basically stuck to the side, hanging there, and it seems like gravity has gone away. That's why they call it the Gravitron. Anyway, for safe operation, the maximum sustained acceleration that riders may experience is 20 meters per second squared, approximately twice the free fall acceleration, so 2 G's. What is the period of the ride when it is being operated at the maximum acceleration? Remember, this is centripetal acceleration, so it's not accelerating anymore. We're moving at a constant speed around the circle. We're feeling at a centripetal acceleration here. And then how fast are the riders moving when the ride is operating at this period? So we got to figure out the period, and we got to figure out the speed that the riders are moving. So 2 parts. Okay, so the first thing we got to do is, it says, what is the period? But to figure out the period, we probably need the acceleration. So A equals, what do we have here? We need the period, so we're going to need the period part of this. So 2 pi over t, and that is all being squared times the radius. Okay, they gave us the acceleration is here. They gave us the radius here, and the only thing we don't know in this is t. So now I'll just solve for t. So first I'm going to divide both sides by r. So now I have a over r. Now I got to square root both sides to get rid of the square. Okay, and that equals 2 pi over t. So now I got to think about how to get rid of, or how to get t by itself. So in order to do that, I'm going to have to multiply both sides by t, and then divide both sides by this square rooted stuff, okay? So that gives me t equals 2 pi divided by square root a over r. Okay, so now I know everything here, so I can plug stuff in. I have 2 pi divided by square root. The acceleration is 20 meters per second squared. Divide by radius is 5 meters. Okay, think about the units for a second here. The meters are both gone. I have per second squared being square rooted. That's going to give me per second, but it's in the bottom. So on the bottom, per second is going to flip to the top and just give me seconds. So this is going to give me the right answer. So now we plug everything in and we find out what the number is. So we have 20 divided by 5 is 4. The square root of 4 is 2. We have 2 on the top divided by 2 on the bottom, which is just 1. So it seems to me like we just get pi seconds. So as a decimal, that would be 3.1 seconds. But we actually got exactly pi seconds for the period, which is interesting. As a decimal, those significant figures, 3.1 seconds. Okay, so now that's the period. And then the second part is how fast are the riders moving when the ride is operated at this period? So how fast means we need a velocity. So we're going to go velocity equals, and now we have our choice of formulas, but we know the radius already and we know the period. So we're going to go with the period version of the velocity equations. So that is 2 pi divided by the period times the radius. Now the period comes out to 3.1 when we use significant figures, but actually we calculated pi. So this is going to be 2 pi over pi times the radius of 5.0 meters. Well, pi divided by pi is gone, so we get exactly 10 meters per second. So that's pretty good. As you go around inside this ride, you're going 10 meters per second. Our little conversion for us, so we understand what this is, would be double it and add a little. You're going maybe around 25 miles an hour. That's pretty fast inside of this thing spinning around. And that's why you wind up stuck to the edge and basically just hanging there. So that's that problem. And now the last thing that we want to talk about here is rank in order from largest to smallest the period of the motion of particles A through D. So we think about this, and always we want to try to apply some sort of formula or some sort of concept to these types of problems so we understand how things change. So the big question is, what formula or idea, concept do we want to use? Well, if you notice in this problem, what's changing is the radius and the velocity, right? And we're talking about period. And we have a formula that involves all three of those. It's V equals 2 pi r over t. Okay, I've written that a little bit differently than it was written, but that's the same formula. Now, we're talking about period of motion. So, and we're changing the velocity and the radius. So what I'm going to do is I'm going to solve for t here. So multiply both sides by t, divide both sides by v. I'm now looking at t equals 2 pi r over v. Okay, so now when we write it like that, we can see that if we increase the radius, the period will increase. If we increase the velocity, that number on the bottom grows, which makes the period decrease. Okay, so that's the idea. Now, every time we increase the radius, the period increases, meaning it takes longer for the object to go around the circle. Okay, every time we increase the velocity, the period decreases, meaning an increased velocity makes the object take less time to go around the circle. So if we're ranking from largest to smallest, the period, we're saying which one goes around the circle the fastest. Okay, so I want to go around the fastest. If I have double the velocity compared to single velocity, compared to the same radius, B will go around the circle faster than A, right? So B is greater period. Sorry, B is a smaller period than A. Let me make sure I'm doing this right. So B is a smaller period than A. Okay? Now, take a look at C and D and compare those. What did we do? We have the same radius, but D is going to go around twice as fast as C is because it has double the velocity. So that means that C has a greater period than D does, okay? D's period is less. So now we want to rank in order from largest to smallest. Which one is going to have the largest period? Well, now if we compare these two here, who's going to have a bigger period here? Well, the one with the bigger radius is going to have a bigger period. If we make the radius bigger, the period gets bigger. So C and D would have larger periods off the bat because the radius is bigger, right? So now we have a general idea of the concept, okay? So if I just use this formula now, if I look at C, I doubled the radius, but I did not change the velocity. Okay, so who has the biggest period here of all of these? C does, because the radius got doubled, but the velocity did not change. So up top here, I would have like 4. On the bottom, nothing changed. Okay, so C is bigger than. Now look at D. D, I doubled the radius, but I also doubled the velocity. So the 2 on top with the 2 on the bottom on R and V would like divide out, and basically nothing changed. It would be the same as A. Here I didn't change anything at top and bottom. The V and the R changed nothing on the formula itself. So D and A are actually the same. So C is greater than D and A equally. D and A are the same. Now B, if you look at B, the radius is the same as A, but the velocity is doubled. So therefore, B goes around faster, like we said right here. So B has to be at the end. It's going around the fastest. So this is the answer to the problem. I know I kind of went around that in a convoluted way, but hopefully that's explaining maybe a little bit more detailed than just saying what the answer is. Okay, so that is the entire section for section 1.